Alright, in this presentation I want to introduce an option which we offer on our website. It's the logic and test probe, and let me tell you the purpose. I'll just show you what it looks like. It's right here. Okay, the logic and test probe was something that we designed in order to determine whether or not a pin, typically on a microcontroller, would need to be lifted or disconnected from the underlying assembly in order for the part to communicate. And you have to realize that when a design engineer designs a microcontroller into a module, they don't expect somebody to be attaching to it externally and reading the data. Okay, so there are pins that are used by the circuit in order to control things. And communicating with an external programmer is not one of those things that they ever expected to do. So, for example, in order for us to communicate, or any programmer to communicate with a microcontroller, in this case we're going to talk about the Motorola family, which are the microcontrollers that we support, which have many design wins because they were the first company that was able to incorporate EEPROM onto the silicon of the microcontroller. But anyway, in order for us to communicate, we need clearly a transmit pin and a receive pin. A transmit pin, if you look at it from the perspective of our product, it transmits data into the microcontroller, and the receive pin receives data from the microcontroller. Okay, but those pins can also be, and this is something that many people don't understand, those are programmable pins, meaning that the code in the microcontroller can reassign the function of those pins. So you can have a pin that will work as a transmit pin or a receive pin, but it can also be programmed as an I/O pin, input-output pin. So if you wanted to use it in your program, which is running on the microcontroller, to like switch on and off a relay or some other physical function, you can do that. Okay, and many times, if they a good design practice, if you're not using a pin, not going to use a pin, you need to tie it to a valid logic level, and a valid logic level is either going to be ground or VSS, which you'll see on the diagrams I'm going to show you, or the positive rail, VDD, which is the +5 supply to the microcontroller. And you weren't ever supposed to tie a pin directly to the power rail. You were always supposed to tie it through a resistor. Well, those resistors, you know, when you're making a product like a module, they cost you a few cents. So many times the engineers will just not do that. Okay, they'll just tie a pin directly to a power rail. Well, if you tie, for example, you're not going to use, let's say, the receive pin for anything, and you just tie it to ground. Okay, so, well, that's a problem, because if we come along and we want to communicate with the part, we're going to require an unencumbered receive pin. So if it's connected to ground, that kind of prevents us from using it to communicate. So the purpose of the logic and test probe was to pre-identify any pins which were not going to be compatible with the signals from the programmer that were necessary for communication. So that's what this does. It performs actually two functions. It has the electronics on it, which will drive a pin and give you an indication that it's going to be compatible with the programmer. But it also has a function called, which allows it to act as what we call a logic probe. Okay, meaning that when you touch the tip of the probe, which is right here, this is the tip of the probe, to a pin with this set to the probe position or logic probe, the LED, I'll show you this in just a second, which is right here, will light either red for a logic high or green for a logic low. Okay, well, why do you care about that? Because on some of the microcontrollers, you have to have external pins, because when the microcontroller is running in its normal application of being the controller of the module, it's using many pins on the periphery of the body of the microcontroller to control things, thus the term microcontroller. Well, in order to get a microcontroller, if it's compatible with communication, meaning we can talk to it, most of them are, many of those pins, which would normally be used to control things, need to be at predetermined logic levels. Okay, meaning that they have to be either a logic high or a logic low before the microcontroller will enter into a communication mode. All right. Some of them are more. There are more pins than you would think would be necessary, but that's the way the part was designed, so you just have to deal with that. But anyway, that is what the logic probe in the probe mode does. You can touch the probe to a pin and determine its logic level, whether it's high or low, okay, 0 or 1, because if it's not at the right level, then you're going to have to force it to that level. But it's possible that with its existing connections on the circuit assembly, it's already at the right level. Okay, so that means that when we show you the wiring diagram, we show you what is absolutely required to get the part to communicate. But if some of the pins are already at the right logic level, then you don't have to put a probe on them and force them to be the level which is assigned. Okay, so that's the purpose of the logic and test probe. The test probe drives the pins to confirm that yes, we can talk to the part. The logic probe allows you to determine in advance whether or not you need to attach a probe to a pin because the pin is already at the right level. Okay, so that's the purpose of this this particular part, this particular item that we have here. So what I'm going to do now, I'm going to hook it up and I'm going to show you basically how it works, and as this demonstration progresses, I'm actually going to show you on a couple of modules it actually operating. Okay, but first I'm just going to show you with the programmer that I have here. The programmer is already powered on. I don't have a part or anything selected because I don't need to in order to show you the probe operating. But anyway, the probe has two connections, which are here, which is the white one is plus and the black one is minus. Okay, I will also tell you that if you hook it up backwards, there's a protection diode on the probe which keeps it from being damaged by reverse polarity. Let me show you something else, because you get, in addition to the wires, we also, in the package, the box in which the probe comes, you get these grabbers. Okay, so you would hook the, if you needed to attach it to, for example, the lead of a part or something like that, you just push these connections onto the pins of the grabbers, and now you can use the grabbers to apply power to the probe, like that. Okay, but what I'm going to do, since we have on our product something which is kind of unique, we have an accessory connector here, and you can attach the probe to the accessory connector. So I'm going to do that. I'm going to put the ground lead over the ground pin and the +5 lead, or the positive lead, over the +5 pin. And what you will see happen if you can see it here, the LED is lit up as yellow. Okay, so we are now in the logic probe state. Okay. Now, if I take the probe, I want you to orient it so you can see it. I'm going to attach it to pin 16 of our socket, which is the ground pin. Okay, watch what happens to the LED. Let me be sure I get this in a place where you can see it. Okay, when I touch it to the ground pin, the LED turns green. Okay, so that's a logic low. All right. Well, because of the way that our product is designed, the next pin up is going to be it's a connection pin, so it's going to be at a logic high, all right, or a logic 1. So when I touch it to the next pin up on the socket, you can see that the LED lights as red. Okay. Now, that's what you do. So you can determine the logic level of a pin on a part by just putting the probe into test mode, and the mode is set with the switch here where it says probe or test. All right, now I'm going to put it into test mode and you can see what will happen. Switch the switch to test, and you see that the LED starts to alternate. It's blinking red and green. Okay, because what it's doing now, instead of testing the logic level at the end of the probe, it's applying a logic level to the end of the probe. And by applying the logic level to the end of the probe, we're able to basically inject it into the pin of the part with which we are working. Okay, and as long as when you touch the pin, if this LED continues to change state, all right, then we are capable of driving, all right, that pin. So you can attach a probe to it and be confident that you're going to be successful in communicating with the part. However, if I'm going to touch it to the ground pin here, which we're not going to be able to drive our logic signal into ground, you will see, I can get the thing into its position here, that the LED locks on low, which is ground. It's locked on low, okay? But if I move it up to the next pin and touch it, we're able to drive that pin, okay? So the LED is blinking, meaning that that pin is successfully accepting the logic level transitions. And although it's not, we're not connected to a part, that's basically how the probe works. Okay, and it gives you the opportunity to, one, determine whether or not a logic level is necessary in the probe mode, or two, whether or not you're going to have to lift a pin or cut a track in the test mode. Okay, so that's what this does. In this case, we're applying power from the accessory connector, but when you're working with a part in circuit, you can, if you can power it from the programmer, but you can also power it from the probes that are attached to the part. So let me get a module and I'll show you how that works. Okay, this is an ECU out of our Mercedes, and it has a Motorola microcontroller in it. It's not in this case, this Motorola microcontroller, which is right here, is not the microcontroller that's it's performing a sub-function in the ECU, probably security, climate control, something like that. This is the processor that is actually running the ECU. This is the memory. I think I may have demonstrated this before in another video. This is a RAM chip. Anyway, if you wanted to clone this module, okay, maybe that's another subject to briefly address. When you clone a module, you want to take the module which is dead. You want to pull the data out of it and put it into another functional module. The modules, in order for the clone to work, both modules have to be the same part number. Okay, you can't clone from one module into another module with a different part number. You could, perhaps, but it's not going to work because the program that is running in the module has to be the same. And if the programs are different, the data is going to be different, and it's not going to work. Okay. there are tools where, you know, hey, we'll clone everything. We'll clone the program, we'll clone the data, we'll clone, you know, every bit of information that's in the ECU. Well, okay, you can do that, but you don't have to in most cases. Why? Because the vehicle-specific data is not in the processor, okay? It's in either an 8-pin EEPROM, which is the most commonplace, or it's going to be in the case of the Motorola microcontroller here, it's in an EEPROM area on the microcontroller. Now, while I'm discussing this, I'll point out something else. There are processors which do have the EEPROM built in. Okay, the Motorola family was the first family that did it. There are some that are available today, Infineon, things like that, you know, manufacturers or parts like that, which have the EEPROM built in. And I'll just cover quickly because I've watched videos. I try to stay current on what's available in the market and what people are presenting, so that I'm aware, and also so that I can be objective when I present information to anybody that chooses to view our videos. Okay, when they clone those, you'll see P data, okay, and you'll see, or I'm sorry, P flash, and you'll see D flash, okay. P flash, P is program, all right. Well, why do you need to suck the program out of a module that's already, you know, working, or that was working, and stick it into a module that is supposed to be working? You don't, because the programs are the same, so why do that? Unless the module is completely non-functional, you should not have to, or virgin, you shouldn't have to copy the program data, because the program data is going to be the same in both modules because they have the same part number. Now, the D flash is data flash. Okay, that's where data is going to be stored, and that will be like key data, the VIN, any parameters that are specific to the vehicle will be stored in D flash, and that would be required in order to clone a module. But you don't necessarily need to read the program memory, because the program memory is going to be the same in both modules. So I wanted to cover that. The other thing that I've seen is C flash. I was trying to figure out what C flash meant. C flash, I guess, is code flash, which is the same as P flash. All right. So I wanted to cover that, so that, you know, that issue. It's something where they don't really talk about it in a lot of videos. They just say, well, we read the P flash and we read the D flash, and then you just put the P flash into the other module. Well, you don't need to do that. Okay, so now that I've discussed that, what I'm going to do is, there's one more thing I want to give you information on, and that is the issue which it's something that happens with all flash parts, all EEPROM parts, and that is fatigue. Okay, an EEPROM part will fail. Okay, if you write to it enough times. Reading it is benign; it doesn't hurt it. It doesn't cause any kind of degradation. But if you program it, what has to happen is the data that's existing on a memory cell has to be erased, okay, and then new data has to be programmed. And the EEPROMs, the original EEPROMs, okay, the 8-pin parts, were far more robust in the way that they were implemented on silicon than the more recent flash parts. And a flash part, with an EEPROM part, you could go in, you could change 1 byte. And that was the only cell in the memory array that would be affected. Okay? And if you want proof of this, look at a solid-state drive today in a computer. Okay? Solid-state drives wear out. They do. There's nothing they can do to prevent it, because there's a layer of oxide that holds the electrons that maintain either a 0 or a 1. And every time you write to a cell, not read from it, but write to a cell, they have to jam the electrons with a high voltage through that insulating gate, and it causes a little bit of degradation. Well, you do that enough times, and those electrons start leaking through the insulator. So they'll do what's called load leveling, where they'll recognize, hey, we've used this area pretty much, so probably got to pick another area. That way we'll lengthen the life of the solid-state drive. So that's what they do. So they'll say there's a little controller in all the solid-state drives that keeps track of how many writes have been done to a certain group of memory cells, and then they'll decide that we're going to move this particular area to another area within the solid-state drive. Solid-state drives are very reliable, okay, but there's lots of extra space in them, which is used to maximize their life by determining the level of fatigue and then moving the functionality into another spot. Okay, well, why does that matter with respect to D-flash? Okay, it matters because, as I said, an EEPROM, you can change a specific location, so only that location is subject to the fatigue. With a flash array, you can't do that. That's not the way they're designed. Okay? With the flash array, you have to erase an entire what's normally referred to as a sector. And you'll see people refer to it as emulated EEPROM. Right. Okay, because what happens is, if you want to change one byte in the D-flash area, you read the whole D-flash area. Okay, you change the byte, you erase the whole D-flash area, and then you write the whole D-flash area back. Okay, and all you did was change one byte. But the fatigue was applied to the fatigue factor was applied to the entire sector. All right, so if you are only writing something that is going to change infrequently, okay, like a VIN, all right, cars rolling off the assembly line, plug into the OBD port, and they write the VIN. All right, well, fine. That goes into D-flash, or if it's an EEPROM-based module, it goes into the EEPROM. But you're not going to find D-flash typically in use in something like a digital cluster. Because with the digital cluster, you're changing mileage. And the mileage changes every time the car moves, okay? So if every time the car moves and they're counting the miles, they're erasing the D-flash area. They would be erasing the D-flash area. And then they would be changing that mileage byte, or bytes, and they would be programming it back, erasing it and programming it back. But the entire D-flash area is subject to the fatigue. Where in an EEPROM, that particular memory structure is fabricated to be far more robust and far more tolerant than the so-called emulated EEPROM. All right, so basically it works in applications where you don't have to write data that frequently, VINs, key information, things like that. Okay. But that's what the D-flash is. When they say it's emulated EEPROM, it's exactly that. They take flash memory and they make it pretend to be an EEPROM. But it's functionally not as reliable or robust as a single EEPROM part, which was designed to function with individual byte alteration capability. All right, well, you've listen to me talk while we've stared at this ECU, but I always want to provide good information to people that take the time to watch our videos, because there's so much stuff on YouTube. I watch these videos and I listen to what the people say, and they're not, intentionally being misleading, but some of the stuff they say is flat out wrong. And, someone that's uninformed, they're not going to know. So I just want you to know. So if you encounter something which is different than, acting in a way different than you expect, you might at least understand why. Okay, so what I'm going to do now, I'm going to proceed with this particular Mercedes module. And I'm going to show you how you know where to connect, first of all, the probe power pins, and then I'll proceed to use the probe. Okay, this is this is our website. It's interesting because this website exists for two reasons. It exists to provide you information and to allow people to purchase our products. That's what it's for. So what I wanted to show you on our website, or if you purchase the communication module, if you purchase one of our kits, Automotive Kit 2 comes with a communication module called the ACOM 2. All right, well, the ACOM 2, in its documentation, has this. I'm kind of not zoomed. I'm zoomed in too far. This is a laminated thing that we use in our lab. But if you look, you can see all of these packages. There's 2 pages, and it's part of the ACOM 2 documentation. So you get this with your ACOM 2. All right, so you know what pins are that you are, which pins are required in order to connect to the part. So you go back to the website, and it's also available on our website. If you want to see it, you can go down here to documentation at the bottom, and then you can go to product addendums, and then you can go up here. Now we have using the logic and test probe, which is a PDF you can download, and this is the sheet that comes with the logic and test probe if you purchase it from us. Anyway, let's see, where am I going here? Okay. Here's the Motorola H680511 adapter, automotive version ACOM 2 right here, ACOM 2 auto.pdf. All right, this is what comes with the ACOM 2. One thing about what we do here, we don't minimize on documentation. You get lots of documentation if you buy from us. So I'm going to scroll down here and show you. I'm going to get to the back. We talk about all the stuff that you can do, how to connect. You'll also notice as we get down further in here, we show you, if you so choose, there's the logic probe, original tool. Okay, then we get down to the bottom, and here come the connection diagrams for the different packages of Motorola microcontroller. Okay, so there they are, and there are 2 pages. There's the first page, and here's the second page. All right, these are the most common ones. If we don't have one, it would be unlikely because most of the ones that we have have been found in modules. But if there's one that we don't have, you can go to the internet and find the data sheet, because all of these package diagrams came from the Motorola data sheets. So what I want to do is, one of the parts that, the first part that we're going to work with is this part right here, the 68HC11E9. Okay, well, I'm going to cover this so that you understand how to identify this particular part, because it's not going to say this on the body of the part. You're going to have what's called a mask number. Okay, and let me bring up the mask numbers here so you can see how this works. I've covered this in other videos, but I'm going to cover it here just to provide you with that information. Okay, here, this is the document that we provide with the ACOM. This is available on the internet. This happens to be our hard copy of the document that we provide. But if you do a search on Motorola mask numbers, there are various places on the internet where you can do a cross-reference, and that's what we're going to do, okay? Because on the top of the microcontroller is what's called a mask number. A mask number is 4 characters which identifies the photo mask that was used to create the part. Okay, so I'm not going to zoom in and show you here. You're just going to have to trust me that it's there. But the mask number in this case, all right, is E28B, E28B. So if you look on the sheet here, the third item says E28B, and then if you look to the right, it says MCU type 68HC11E9. All right, so that's how you know what the industry standard part number is with which you are working. Okay, because very rarely, sometimes they'll print the industry standard number on them, but not usually. Okay, and the reason that they don't print the industry standard part number on them is because the program that's running in the processor was placed there when the processor was fabricated. Okay, so yeah, it's a 68HC11E9 architectured part, but the program memory, if you have another E9, which is in a different module from a different manufacturer doing a different thing, the program's going to be different. So the mask number that was used to fabricate the part is going to be different. All right. So, but that's the document that you use, or the information that you use to locate the mask and then locate the actual industry standard part, which you're going to need in order to connect to the part. Okay, so here we are looking back at the part, and although I'm not going to zoom in on the part, I will tell you that pin 1 is indicated by a dimple right here on the part, and then the pin numbers go around from the left down the side, across the bottom, back up here, and they end here. Okay, this is what's called a PLCC part. Okay, PLCC is plastic leaded chip carrier, and it's also called a J lead because the leads, they come out of the body of the part and they loop underneath it. Okay, so that's the way that the part is fabricated, and if a pin has to be lifted, the way that you do it is that you get your dental pick and your soldering iron, and you put the dental pick underneath behind the pin that you need to lift. You heat up the pin and you gently with the dental pick rotate it, and the lead will come out from under the part, and that will disconnect it from the underlying assembly. So that's how you lift a pin. Okay, and then when you're done, after you've connected the probes to it and you've read your data, you just push the pin back down, heat it up with the soldering iron. You might have to add a little solder, but many times you don't. Solder will liquefy and the pin will be reattached to the assembly. Okay, so that's what's necessary in order to lift the pin. Now, let me show you the connections to the part. Okay. This is the part in the documentation that we provide, and I'm just going to go over what the what the pins are so you understand. Okay, VSS is ground. That's your ground line. That's 0 volts. All right. 1 is this, or pin number 2 is a mode pin, but it's also got this alternate function standby. Pin number 3 is also a mode pin, and I'll tell you what the mode pins do on this part. Okay, the mode pins, one of the modes that it goes into is communication mode. All right, and in order for the communication mode to be active, both mode pins have to be at 0 volts. Okay, and if you look down here, we show you, all right, ground, which is the blue probe, and violet, which is also, in this particular case, going to be at ground. There's a switch on the ACOM which lets you choose this. And also here, since this is the ground pin, we have the red probe. So we have all of our probes attached to these 3 pins to provide the ground signal. Okay? Now, on this particular family, in its normal operating mode, one of the mode pins is typically going to be at 5 volts because that's the mode that it needs to be in order for the program not to be in communication mode, but the program needs to be in I'm a controller of whatever the module is mode. Okay, so what'll happen is if the engineer that designed it used good design practice, he will have tied that mode pin to 5 volts through a resistor. But if he didn't, okay, if he went the cheap way and he just tied it right to the positive power rail, and you hook up your ACOM, okay, with both of these grounded, the power rail, which is at +5, and the mode pin, which we are now forcing to ground, are hooked together. And what happens if you hook the positive power rail and the ground rail together? Well, you've shorted out your power supply. That's what happens. And with our product, although we're current limited, what you will see is there's a power light on the ACOM adapter indicating that it's on. There's a switch when you turn it on. That's shown in other videos that we've done. But if you turn the switch on and the light doesn't come on, you've got all your probes hooked up, that's kind of what we call a clue that you got a problem here, and it's not coming on because there's a short. And this is, you wouldn't have, if you would have used the logic and test probe, you would have identified this in advance, okay? But in the event that you didn't, that's kind of a clue to indicate that, yeah, you've got an overloaded power supply. Okay, so the mode pins determine the communication mode. They have to both be at ground for this particular part. Over here we have the clock pin. This is where we send the clock signal into the part to establish its operating frequency. Down here on pin 17, and that is the yellow probe. Pin 17, we have the reset line. Okay, and this is where we reset the processor so that it is going to start at the place where we want it to look to see if it needs to communicate, and that's the green probe. Okay, so we send a reset pulse to the processor to get it to start, and down here we have the 2 communication lines. On pin 20 we have the transmit line, which is orange, okay, the orange probe, and then on pin 21 we have the receive pin, which is a brown probe. Alright, then over here we have VDD, yes, labeled correctly, which is the positive supply rail, positive power supply to the part, and that is +5, which is the gray probe. Okay, these are the only connections that you need in order for this part to work. Alright, but remember, this part is soldered to an existing circuit assembly with existing components. Things that are already hooked to all of these pins. Okay, as I said, the designer didn't expect you to be coming along with your Andromeda research tool and the ACOM2 adapter and connecting probes to, this part in order to extract data from its EEPROM array. So, can you do that in circuit? Absolutely. Did he design it so you could do that in circuit? Well, it would be nice if he did, but perhaps not, and that's where we end up using the logic and test probe. Okay, now I'm going to show you one other part which would be more indicative of using the logic probe, and I'm going to do that just a minute. Okay, this is a security module out of a Mercedes. I think it's a Mercedes, probably from the 90s. But anyway, nonetheless, it has a Motorola microcontroller on it, and it is right here. Okay. The mask number, I'm just going to show you the mask number, or tell you the mask number. The mask number is D60J. Okay, got my paper over here, so we can't get this lined up. Probably not going the way that I exactly want. Anyway, the D60J is right here. And it is a 68HC05B16. Okay? That's not an 11 family. This is an 05 family, and the 05 family was not as quite as sophisticated as the 11 family of microcontroller. But anyway, I wanted you to see it, and well, I don't want to spend a lot of time going through probing parts. but I did want you to see that this is a different part, and you can communicate with it, assuming that there are no pins which need to be lifted or will cause interference. But let's switch over now, and I'll show you the pinout for this particular device and for this particular microcontroller, and why the logic part of our probe would be valuable to you. Okay, this is the connection diagram for this particular part, 68HC05B6 and B16. So that's what the device is on this particular module. You'll notice that the pins are not in the same place as they were on the previous part. Okay. However, the colors are the same, and the pin numbers are the same, where they start with the pin 1 here, and then they go down and around and back up the side to here. All right. So anyway, in this case, the receive line, the brown probe, is on pin 52, and the transmit line is on pin 50. And look here, we have VDD, which is the positive supply rail, is on pin 10, and we have VSS, which is the ground supply, is on pin 41. Okay, so we have VDD is the gray wire, and the ground is the blue wire. All right, but look at all of the other connections that are required. Okay, we've got to have ground on pin 9 in order for this to work, and that's just an input pin. Okay, it's either an I/O pin or it's an analog pin. That's what the AN stands for. And we have to have 5 volts, so this has to be at ground, and then we have to have 5 volts on pin 11, which is gray. Okay, so we indicate gray as being in attached to multiple places, and this is one of the things I'll just show you real quick. If you get the ACOM adapter, you'll get our probe extensions. Okay, and this is what the probe extensions are for. You can hook these probe extensions to other probes, meaning you can hook, like the white one to the gray probe, and then the black one to the white one. So you have multiple connection points available to you. So, because if we only had the one gray probe, and yet you had a controller where you needed to have 5 volts applied to multiple pins or other signals applied to multiple pins, you wouldn't be able to do it. So we provide these probe extensions as part of the ACOM2 package. Now, so we've got 5 volts here, ground here. We have the what's called oscillator. This is where the clock goes in. Okay, the yellow wire is always the clock. Then we have the reset pin, which again is green. On pin 18, we have the 9-volt pin. This part requires the application of 9 volts. The ACOM2 adapter provides a 9-volt source, so that you'll be able to attach the 9-volt source to pin number 9, and there's a switch on the ACOM adapter which changes the functions of certain pins, so that in some cases it's ground, in some cases it's 9 volts. So we give you all of the options from which to choose, and then again we've got to have 5 volts on pin 22. Okay, so you can see that if you were to use the logic probe in the logic probe mode, you could, before connecting and seeing if you could communicate, or even testing to see if you needed to drive a pin, you could go and you could test these in advance to see if perhaps the logic level on this particular pin was low. And if it is, then you don't have to put a probe there. You can check it on pin 11. If it's high, you don't have to put a probe there. If it's not high, then you would switch the probe into test mode from probe mode and see if we could drive the pin. Okay, meaning would it alternate between red and green, meaning that then you would be okay to apply a fixed logic level to this pin, and that would work. Okay, but you could do that. Clock is not one where you have to test it for a logic level. Restart is not one where you have to, or reset is not one where you have to test it for a logic level. The 9-volt source is not one. But down here on pin 22, we have, the signal is called T-cap, which may have something to do with an internal timer on the part, and that has to be at 5 volts. Okay, so the logic probe would let you predetermine whether or not you had to apply a signal to those pins in order to get the part to communicate. So that's what I wanted to point out. In this particular device, there are 1, 2, 3 pins which have to be at specified logic levels before the part will talk. All right, and that's in order to get the part out of its normal mode of controlling the module and into a mode where we can communicate with it. So that's one place where the logic probe function gives you the opportunity to determine whether or not you have to even put a probe on the pin. So that's what I wanted to show you about this particular module and this particular part. There are many modules that have Motorola microcontrollers on them. Okay, and the logic and test probe will work on any of those modules. And now what I'm going to do is I'm going to go ahead and show you with the original Mercedes module that I had. Okay, I've got the probes on this part on the module, and again I've got the red probe is hooked to pin number 1, okay, and the gray probe is hooked to pin number 25. But as I said previously, the probes, they have 2 connection points. Okay, let me switch over to the where I've got the probes attached, and you can see that. Okay, if you look here, you can see that I've got the black negative connection from the probe on the other side of the probe. Okay, so I got the red probe, red wire here, which feeds the ground signal to the red probe, and then I've got the black negative connection to the probe itself. Maybe I should call this the grabber, to the red, the opposite pin. See, there's a pin on each side of the body of these grabbers. Okay, and the same thing is true for the positive supply. The gray wire, scoot this down a little, or up a little, I mean. The gray wire is hooked to one side of the grabber, and the white wire is hooked to the other side of the grabber. Okay, and the grabber snout or end is attached to pin 26, which is the positive supply to the processor. So in order to make this determination, you got to have power to the processor. I don't even have to select the processor part number. Okay, I just need to apply power to it. The other probes are just laying here on the bench. They're not hooked up and they're not used because we're going to determine in advance whether or not we have to do any preliminary pin lifting in order to allow this to communicate. Okay, so where it's attached to the ACOM2, here's the probe. All right, and I'm going to put it into it's in test mode, and I'm going to turn on the ACOM2. The ACOM2 is a switch. If you've watched our other videos and you've watched how to use the ACOM2, you hook things up to your part and then you turn it on, so you're not hooking things up hot. All right, so I'm going to turn on the switch to the ACOM2, and you can see that the probe now is alternating between the high and low logic levels, which it is applying to the tip of the probe. Okay, so what I'm going to do now is I'm going to test each one of the pins to confirm that we are going to be successful. All right, so we're going to start with pin number 2. I hope this works the way that I expect it to. I'm going to zoom in so you can hopefully see it better. We're going to hook it to pin number 2. And we're good on pin number 2. The LED is continuing to flash. Hook it to pin number 3. We're good. The LED is continuing to flash. We're going to hook it to pin number 7, which is the clock, which would be very unlikely because that's normally where the crystal feeds into the processor to establish its frequency. That's fine. We don't have to do any lifting there. Then we're going to move down to the reset pin, which is pin 17. So we're going to go 20, 19, 18, 17. Put the probe there. Continuing to flash. Now we're going to go to pin 20, which is the transmit pin. Okay, pin 20 is right here. And we got a problem. Okay, on this module, pin 20 is grounded. All right, so they didn't use the pin for anything in the circuit, so to keep it from floating or not being connected to anything, they grounded it. Okay, so that pin's got to be lifted in order for this particular module with this processor to communicate. All right, so we've just identified a pin which we would need to lift. All right, now let's move over to pin 21. Pin 21 is continuing to flash, so we're good on pin 21. All right, that's the receive pin. So before we've even attached the probes or made an attempt to communicate with this module, we know that we have to lift pin 20. All right, now what I'm going to do is I have another module where we've lifted pin 20. I'm just going to show you what it looks like to have that pin lifted so you've got a reference. Okay, but that shows you why you would use the probe in order to determine in advance whether or not you needed to lift a pin. Now the other thing we can do, let's test for logic levels on pins 1 and 2, which are mode pins, which need to be at ground. Okay, so we're going to have I put the probe into probe mode, logic probe mode, and it doesn't appear as though there is anything connected to pin number 2. So we are good on pin number 2. So we can ground that pin and it won't cause a problem. Pin number 3, if you look, you can see my thumb's kind of in the way here. Pin number 3 is already at ground. Okay, so we actually wouldn't have to connect a probe there. If that pin was at a different logic level, then we would. If it was at a logic high, then we would probably have to lift it, because that meant that the designer connected it to the positive rail of the power supply, and that would short out the power supply. Okay, so that's on pin 3, where you can see it's grounded. Oh, there we go. I didn't have a good connection on pin 2. Okay, pin 2 is actually at a logic high. Okay, so let's see if we can drive it. Put the probe back over to test mode. Yes, the guy that designed this module did it correctly. Okay, so pin 2 has also got to be at ground, but its logic level, when we go to this test mode, why am I not able to flip this switch? There we go. Is high. Okay, so it's a logic 1, but we can drive it to a logic 0. We know that because the LED is flashing. So we don't have to do anything. There's only one pin on this particular module, on this particular processor, that needs to be lifted, and that's pin number 20. All right, so that shows you how the logic and test probe allows you to evaluate in advance whether or not you're going to have to do any kind of pin lifting, because, as I said, there are many thousands of modules. Bunches of them have Motorola processors. This is just one particular family of processor and one particular module. But the logic and test probe gives you the opportunity to determine whether or not you're going to have to do any preparatory work, preliminary work, before you actually connect all the other probes and attempt to communicate with the module. All right, so that shows you what I wanted to show you with respect to the probe when it's used with Motorola microcontrollers. Okay. However, the logic and test probe can also be used with EEPROMs. It's very rare that you would need to use this with EEPROMs, because most EEPROMs were able to drive the electronics on the circuit assembly through the pins on the EEPROM. We're very good at doing in-circuit work with EEPROMs. But there is one case, and I'll show you that in just a second, where it can really cause an issue if you're not aware of the situation. So let me get my two modules, and I'll show you that case. Okay, this is the module where it's the same processor, same kind of module, but where we've lifted pin 20. It's right. Don't know that I'm going to be able to get in here with my pencil without knocking this thing off. Right here. Okay, that's where it's lifted. And if you look at it closely, you can see that all we did was we just heated it up with a small soldering iron, put a dental pick behind it, and then levered up the leg. Okay, about maybe 30 degrees. Now, after the leg is levered up, what you can do is you can put a little piece of paper or some insulator under it if you want to be sure that it doesn't connect back to the pad while it's disconnected. Okay, you can do that. A lot of time for a PLCC package like this, it's usually not necessary. For a quad flat pack, you might want to do that. But anyway, then you would put the probe on that leg after it's been lifted, and then you would be able to communicate with the part. Okay, so I wanted you to see that the leg has been lifted. I hope you can make that out, but it's pretty clear. It's just lifted out from the underlying pad, and then once you're done, you just push it back down, heat it up, and it should the solder should reliquefy and it should reattach to the pad. Okay, so that's what would be required in order to lift that pin. Anyway, let me move on. I want to show you an EEPROM application for the logic and test probe. Okay, before I move on, I wanted to show you this. Some of you who are watching might say, well, you showed us how to connect the logic and test probe right to the accessory connector before. Why don't you do that again? Well, when you're dealing with the ACOM itself uses the accessory connector, the orange wire right here, to connect to 5 volts, because we supply 5 volts to our ACOM adapter. The EEPROM Plus system uses adapters. We don't try to design all of the switching signals for all of the many chips that we support through one socket. Okay, so we have adapters. And the ACOM to adapter gets its 5 volt source from the accessory connector. So the 5 volt pin was not available to connect the logic probe. So I just wanted to throw that in here before I hook up or show you the EEPROM. Okay, before I hook up the probe to an EEPROM module, I wanted to give you a little bit of background about why what I'm going to explain to you is important. Okay, there are 3 families of EEPROMs which you normally encounter in vehicle modules. There's the 93 family or 93C family. C just means CMOS technology. LC means low voltage CMOS technology. Then there is the 25 family. 25 or 95, both of them are the same. The 95 family is different. It's a different part number, but it's exactly the same family. It's just made by SGS Thompson, where the 25 family may be made by Atmel or Microchip. Okay. SGS Thompson did not want their numbers to match other people's numbers, so they assigned the 95 to it. And the third family is the 24 family. Okay, the 93 family is known as microwire. The 2595 family is SPI, or as some people call it on YouTube, SPI. And the 24 family is I squared C. Not I2C, I squared C. It means integrated circuit, I squared C. Anyway, the one that I'm going to show you now is the 93 family. And the 93 family is the only member of, or the only family that supports two internal organizations of the memory array. Okay, why is that important? Well, it's important because depending upon how you read it, if you read it with the incorrect driver, you will get what appears to be valid data, but it will not be valid. Okay, and let me explain why that is. Okay, if you look here, this is a pinout of a typical SOIC or DIP package. 93C, this is a 7686 data sheet. The EEPROM on the model I'm going to show you is going to be an 86, but it doesn't make any difference. The 76 is a 1K part, the 86 is a 2K part. Anyway, if you look here, you see the power pin, VCC, which is incorrectly labeled, pin number 8, VSS, which is ground. Okay, and then you've got your communication pins over here, chip select, clock, data in, data out. But then you have one here on pin 6, and it's called org. Okay, org means organization. Why is this important? Okay, because this family, and only this family, supports two internal memory array organizations. It doesn't change the capacity, storage capacity of the part. It just changes the way that the data goes in and out. Okay? Meaning that, if you look over here on this data sheet, it says org. Okay? Org pin, selectable memory configuration. Alright? 1024, this is for the 93C76. Let's stick with the 93C86. 2048 by 8. Okay, that means 2048 8-bit bytes. Or 1024 by 16-bit. Okay, 16-bit bits of data are typically called words. Okay, so you've got 2048 bytes or 1024 words. It's the same number total of bits, but it radically changes the way that a programmer talks to a part. Okay, because if the part is configured for 8-bit mode, okay, and you read it, and you're reading it with a 93C86 selected part, which is normally a 16-bit part, and you read it, but it's in 8-bit mode, you will get data out. It will give you data. Because as you're requesting the data from the part, its little internal state machine, which controls the sequencing of its internal logic to deliver the data as you are requesting, it gets all confused. Okay, because you're asking it for 16 bits, but it's configured for 8. So it goes, okay, here's your 8 bits. And you're saying, I want more bits. I need 8 more bits because I'm reading a 16-bit part. So it starts to choke and struggle, and it will give you 8 more bits of data. Where they come from, who knows? But it will do it repeatedly every time. Meaning if you read it with the incorrect driver, it'll give you the same bad data every time. Same holds true if you read a part which is configured for 16 bits, which is its normal configuration. Okay? If the engineer does not hook up the organization pin, it will normally revert to a 16-bit configuration. Okay, meaning that it will give you 16 bits. When you ask it for the contents of a memory location, it will give you 16 bits. If you are programming it, you must give it 16 bits in order for it to program correctly. Okay, so, but then if you turn around and you read the part as an 8-bit part, but the org pin is not connected, it's not grounded, okay, or if it's high, and you read it as an 8-bit part, you'll get the same corrupt data that comes out, but it'll be incorrect. Okay? So what you need to know before you start reading parts, is it an 8-bit part or is it a 16-bit part? Is it organized internally as 8 bits or is it organized internally as 16 bits? Okay, well, it depends on the logic level which is applied to pin 6. All right, if pin 6 is unconnected or high, then it'll be 16 bits. If pin 6 is grounded or low, then it will be 8 bits. As I said, the internal storage capacity is the same. It doesn't change anything, it just changes how you communicate with the part. All right, so the reason that it's important for you to know is you can read this part and you'll think, oh, look at that, got a good read. And then you go to move your clip over to another module and you try to program and it'll say device did not program correctly. Okay, because although you can read the parts, they will not program. You can read the parts and they'll give you bad data, but they will not program. They will always fail when you try to program it if it's in the wrong mode. Meaning if you have read the part as a 16-bit part, even though it's an 8-bit part, and you move over to your target module and you try to program it as a 16-bit part, but it's an 8-bit part, it'll fail because it doesn't know what to do. Basically, you're sending it 16 bits when it's expecting 8. It gets all confused, and it doesn't program correctly. Usually it doesn't corrupt the part. It can, but usually it doesn't. So that's the reason I'm going to show you how to tell what the configuration is of the part in circuit. Okay, if you take it out of circuit, with the exception of a few microchip parts, okay, the microchip makes some of these parts where they're locked as 8 bits. Otherwise, if you take it out of circuit, well, what happens? You take it out of circuit and the org pin floats high because internal to this part is what's called a pull-up resistor, which pulls it up to the logic level of the power pin, and it always reverts to 16-bit mode out of circuit. Okay, but if you have it in circuit and the designer grounded pin 6, forcing it into 8-bit mode, then it'll require a different driver. You got to use an 8-bit driver to talk to it as opposed to a 16-bit driver. Now, I'll just give you a little insight. Why would you want it to be organized as 8 bits versus 16 bits? They do it for the convenience of the person writing the code. Okay, if you're using an 8-bit microcontroller, the 8-bit microcontroller is going to be much happier, and the guy programming the 8-bit microcontroller is going to be much happier if he doesn't have to read 16 bits and then divide that into an upper byte and a lower byte. So they can force the organization of the part into an 8-bit mode, so all he has to do is ask for a specific byte from a specific address and it comes out with the correct number of bits, and he doesn't have to fiddle around with splitting it into two bytes. So that's why the org pin is there. Also, originally, a long time ago, when the microwire family was created by National Semiconductor, there was no org pin. Parts came, they were 16 bits. You didn't have the opportunity to have an 8-bit organization. But as time passed, and engineers, they got extra pins, had pin 6 and pin 7 available to them, so that you just bothered them that there were these extra pins and they didn't do anything. So they added the org pin. Okay, org pin's been around for quite some time. I'll just tell you, PE is program enable. It used to be, there was no external write protect pin on the 93 family of serial EEPROMs, but there is now, I guess some companies have added this. Normally it doesn't, it's very rarely used. Okay, it's a hardware write protect. Okay, so if it's high, then the program is enabled. If it's low, then you're not going to be able to program it. One more bit of information. The 93 family is the only family that has two modes, has an 8-bit and a 16-bit mode. Both of the other families are 8 bits only. The 2595 family, the SPI parts are only 8 bits, and the 24 family is only 8 bits. So it only applies when you're dealing with the 93 family of serial EEPROM. Okay, I'm going to hook up a module, two modules. I've got one with an 8-bit configured part and one with a 16-bit configured part. And I'll show you how we use the probe to make that determination. Okay, this is a Kessie module out of the Volkswagen. Don't ask me the year. It's out of a Volkswagen. It's one of the, it's the security, the immobilizer module. Anyway, it's got a 93C86 EEPROM. And that 93C86 EEPROM is right here. It's the 93C86. Okay, I'll zoom in so you can see it. Okay, zoomed in so you can see the part. Let me point out, here's the part right here. And if you look, you can see pin 1 is in the upper left-hand corner here. They mark it with a little dimple. And then pin 5 is here, and pin 6, oops, wrong, pin 5 is here, pin 6 is there. And if you look closely, you can see that there's a trace. See the trace that's connecting pins 5 and 6. Okay, so yeah, this is forced into 8-bit mode, which, you know, if you want to get out your magnifier and look, you can tell if you see a trace between pin 5 and 6 that it's in 8-bit mode. You wouldn't need to use the logic and test probe, which works fine unless pins 5 and 6, the connection is underneath the part, in which case you can't see it, and you assume that it's a 16-bit part, but it's not. Okay, just in this particular case, pins 5 and 6 are, you can see that between them there is a trace that hooks those two together. Okay, so I'm going to show you what happens if you read a part with the wrong driver. So let me get that set up. Okay, I've attached the clip to the part. The programmer is set up. I'm not going to show you the programmer. It's got the uncircuit adapter in it. If you watch any of our videos, you've seen this more times than you probably care to see it again. But the computer, I've got our software running. Here's that. It's set up, as you can see, for 93C86. But, as I showed you, this is an 8-bit part. But I want you to see what happens when I read it as a 16-bit part, because that's what's going to happen here. So I'm going to go to Command 5, and I'm going to say, let's clear this. That's from when I confirmed that it worked. It was supposed to work. And you press G for Get Valid Data, and it's going to read it. And it's going to compare it, and it's going to come up, and it's going to say part and buffer match. Okay? Data indicates valid. But it's not. It's not valid. And I kind of give you a clue as to how sometimes you can tell. Okay? Look here. You see these FF7F, FF7F, FF7F. This is where the part says, I don't know what to give you, so I'm just going to give you a bunch of 1s, which are FFs are all 1s, 7Fs is 0, 1, 1. So if you see a bunch of FF7Fs in your data field, it's kind of a clue that maybe this isn't right. But you'll see that in this case, the little EEPROM is just chunking out incorrect data twice, because that's what Command G does. It reads it, then it reads it again, and it compares. And if they match, then it says part and buffer match. Data indicates valid, because the program doesn't know, but it's not good data. Okay, so that's what happens if you read an 8-bit part as with a 16-bit configured driver. Well, with our software, we can change it. Okay, so we're just going to get out of the buffer editor, go to Command 9, and we let you change it. 93C86 dash 8-bit. 8-bit. Okay, that's how you pick the 8-bit driver. All right, and when I select the part, you'll see up here in the corner it will say 93C86-8-bit. Okay, now let us read the part with the correct driver. Command 5, get valid data. Well, that is a little bit different, isn't it? Okay. So, matter of fact, I think we've got a VIN here. Maybe not. Anyway, that's not the point of this. So with the correct driver, the data is correct. It comes out, it's correct. Now, how would you know? You look at the part, if you're unaware that there are two different, configurations available, how would you know which one to use? Because on the top of the part, it doesn't say 93C86-8-bit, it says 93C86. So otherwise you would not know. Okay. So, what I'm going to do now, I'm going to show you how to use the logic probe in logic probe mode to make this determination. All right. So I'm going to hook up the probe the way that I did initially with the white and black, the positive and negative wires hooked to the accessory connector. So let me do that, and then I'll show you how we're going to confirm that this is an 8-bit part. Okay, the way that we're going to connect, since the clip is already on the part, you can't take the logic test probe and touch the pin directly on the body of the chip itself. However, the clip has, I'll show you right here, where the pins here they slide into the body, and then they make connection to the little brass fingers down here, but they do it through these little access points here. Okay, maybe I'm not showing this correctly, but we have basically openings in the body of the clip which allow you to go in and touch the appropriate pin of the clip, or you could slide the connector off of the pin slightly and touch it there, but these are really convenient. You can touch it right there. Okay, so what I'm going to do, I'm going to show you, this is a clip that, let's see, got a red dot here, okay, and if you turn it this way, which is the way that it's oriented on the assembly itself, then we're going to go and access the openings which are here and here. Okay, that's ground, and that's pin number 5 and pin number 6. All right, so let's do that. Here I've got my logic test probe. It's set in this case to logic probe mode, so you can see that the LED is yellow. And now I'm going to touch it to pin number 5, which is ground. Okay, you can see that the LED turns green, which is low. That's ground. All right, I'm going to move it up one. Here, pin number 6. It too is ground. Okay, so we know simply by using the logic and test probe in advance, we didn't have to do any, anything special with the software. We just selected the part, and then we touched those pins once the clip was attached, and we did, confirm that we were reading data out of the part, so we know that the connection is good and all of that. But we now know that we've confirmed, based on this, the logic level on pin 6, that this is a 16-bit part, or I'm sorry, an 8-bit part, not 16 bits. If that pin was unconnected, you'd have this. All right, you'd have basically an open pin, or it might be a logic 1. Sometimes the engineers will connect it to the positive supply. It might be a logic 1, but if it's a logic 0, then it's an 8-bit part. This would also work in the test mode. Okay, so if I change the logic test probe to test mode, and I go in and I touch pin number 6, you see it also stays at a logic low. So that's how you would use the logic test probe to determine whether or not a part was an 8-bit configured part or a 16-bit configured part. I'm going to get a module which is a 16-bit configured part, and just show you. Okay, this is an ECU out of a 2017 to 2019 Subaru BRZ. The point of this, one thing you should recognize from this, EEPROMs are used. They're used in a variety of different modules, ECUs. Not everybody may use an EEPROM. It's up to the design team, but they are still a very widely used part. Okay. Anyway, this is a 93C86, but it's a 16-bit part. Now what I've done is, let me switch over to the computer screen here. I've configured our software 93C86-8-bit. So I'm going to read it using the wrong driver. Okay. So let's go ahead and do that. Command 5, Command G. We're going to read it. And that's what we see. Okay. Now, another thing, if you look here, here we have double characters. HH, PP, DD, AA. That's kind of 66, 1133. That's kind of an indication that data probably is not correct. Okay. So we've read it with an 8-bit driver. Now this part, when you would find this part, it would say 93C86. You would select the 93C86, which would be the 16-bit configured part, and it would work. Okay. But I'm still going to show you that if you read it with the wrong driver, it works. It appears to work. Data's wrong, but it appears to work. So what we're going to do is we're going to change this part to 93C86. All right, and use the right driver. Now let's go back to Command 5, and we're going to say get valid data. Well, that's a bit different. Okay, and that is correct data. That's good data. That is 16-bit data that's been delivered from a 16-bit configured part. Okay, so now I'm going to attach the logic probe and touch it so you can see. Okay, something that I neglected to do when I showed you the KESI module, I did not power up the chip. Okay, basically I had the connector on it and we read it. But when we read a part, clearly we have to power up the chip in order to accomplish that. Well, what can happen is if the circuitry on the assembly has no power applied to it, you can have what will be an incorrect logic level that will appear on pin number 6. So I should have powered up the chip, and I'll show you how we power up the chip using our product. Let me get over to the main command list here. Escape out of here. Well, I didn't need to escape. Go back to the buffer editor. We have a command called inspect. Okay, the inspect command it's like quick view, except when you invoke it, you press I, it powers up the chip so you can inspect different areas. I don't want to go into too much detail on how the inspect command works, but when you press I, it will power up the chip and leave it powered on. Okay, you'll see the socket power light come on, which means that the power to the assembly is available. It's active. Okay, so I'm going to power up the assembly. I guess one way to show you would be this. Okay, let's do this. Let me go back to the module. I'm going to put my logic and test probe on pin number 5. Okay, and it turns green, which means it's low. I'm going to put it on pin number 6, and it turns green, which means that it's low. Well, what? But it's a 16-bit configured part. How can it possibly be low if it's 16 bits? Well, there's no power to the assembly right now. So what we have is basically the ground capability feeding through other components on this assembly and causing an apparent logic level of 0 to be on pin number 6. But if I switch the probe to test, you'll see we can drive the pin. Okay, so it's not really grounded. All right, it's just that the underlying circuitry is causing the probe to see a logic low. But I'm going to switch back to logic probe mode. Now I'm going to press inspect, which will power up this assembly, and watch what happens. Okay, when I press inspect, press I, you see that the LED changes to red. Okay, so it goes high. All right, so that's the indication. The ORG pin is now a 1 since power is applied to the assembly. So the chip is configured in 16-bit mode. Sorry, I didn't mean to confuse you there, but that's my fault. So you need, when you do a test with the chip and circuit, you need to power up the assembly. Once you've got the clip attached, you're able to read data using the inspect command. Okay. Anyway, that pretty much wraps up what I wanted to show you with the logic and test probe. This has gone a bit longer than I had anticipated, but I hope you found the information useful. I hope you understand 8-bit mode, 16-bit mode. It just applies to the 93 family. And real quick, I'll pull the programmer over so you can see this happen. Okay, here's the programmer. If you look, these are our LEDs that show status of things. Okay, you got the green power light. But what I want you to see is when I go over to the computer, and I'm going to press the inspect key. I'm pressing it right now. Okay, you see the socket power light, the yellow LED lights up. All right, and to turn it off, I can just press escape and it'll exit the inspect mode. Okay, so the light goes out. Inspect, the LED comes on, escape, the light goes out. Or if I do like a quick view, I guess I still am connected to the port. I don't know if this will work. Watch the LED when I do a quick view. And it goes out. Okay, so it reads the information from the part and then powers it off. So that's how our product works. You can always tell what's happening just by watching the socket power light. If you ever instruct the programmer or the software to do something and the socket power light doesn't light up, then you're not communicating or controlling the programmer. Okay, well that wraps up what I wanted to basically discuss and present in this video. As always, if you like this content, you can subscribe. We would appreciate it if you give us a like. It kind of allows our videos to be promoted by YouTube. As I've said in the past, we're not a big business, and anyone that would be interested in acquiring one of our products or acquiring the logic test probe or any of the other options that are available on our website, we would sincerely appreciate your business. Helps us keep the lights on here. And also, if you buy from us, we do care about you as a customer, and we will always give you the best guidance and assistance that we possibly can. So if you would like to talk with us, we have a phone number, and we have an email address, and all of that information, including everything that we offer, is available on our website. And that website is arlabs.com.